Here we have a holiday special, the integral from 0 to pi by 2 of e to the cosine of x. Now this is quite fascinating. Now since we can't find any antiderivatives, we're going to have to make use of a very handy property of the exponential function. I'm talking about its series expansion. Now e to the x can be written as the sum over all non-negative integers k of x to the k divided by k factorial. Now in this case, we have to replace x by the cosine of x. So we have the infinite sum over all non-negative integers k of cosine to the k of x divided by k factorial. So let's call this integral I. And this series expansion implies that we have the integral from 0 to pi by 2 of the infinite sum over k of the cosine of x to the k cosine to the k of x divided by k factorial. Now here's the golden question. Can we switch up this integration and the summation operators? Can we switch up these operators? Well, that depends upon convergence. Now notice that we have e to the cosine of x, and the cosine of x is a bounded function anyway. So we shouldn't have any problems with convergence whatsoever. And if you have a convergent series and you're integrating a convergent series, you may switch up the order of the summation and integration operators. So we have the sum over k, the infinite sum over k of the integral from 0 to pi by 2 of cosine to the k of x divided by k factorial. Now this is actually quite useful because as far as integration is concerned, the k is a constant, so you can take it outside of the integral. So we have the sum over k of 1 by k factorial times the integral from 0 to pi by 2 of the cosine to the k of x. Now we can make use of a reduction formula here. If you're integrating from 0 to pi by 2, the cosine of x to the nth power times the sine of x to the nth power, then all of this reduces to the gamma function of m plus 1 by 2 multiplied by the gamma function of n plus 1 by 2 divided by twice gamma m plus n by 2 plus 1. So here we have to replace m by k and n by 0. And in doing so, if you replace n by 0, you have gamma 1 by 2, which evaluates quite nicely to the square root of pi, of course. So all of this implies that I equals the infinite sum over k of 1 by k factorial times this integral, right, which evaluates to all these gamma functions. So we have gamma k plus 1 by 2 times the square root of pi. So let's write it up here. Divided by 2 times the gamma function of k by 2 plus 1. And immediately we can use a recursive formula for the gamma function. We know that gamma x plus 1 equals x times gamma of x, right? Sorry about that. So x times gamma x. So if you have gamma k plus 2, k by 2 plus 1, this equals, let me just note this in a different color, this equals k by 2 times gamma k by 2. And we have a 2 being multiplied here as well, so they just cancel out. So all of this further implies that I equals the infinite sum over k of square root pi by k factorial times gamma k plus 1 by 2 divided by gamma k times gamma k by 2. So we've reduced a problem of integration to a problem of an infinite sum, an infinite series. And it involves a few gamma functions here and there. But gamma functions have really fun properties, which is why I love working with them as well. So let me just take this constant term outside the sum, square root pi outside, sum, infinite sum over k, and you have 1 by k factorial times this k term as well, multiplied by gamma k plus 1 by 2, which is going to be quite interesting for us later. times gamma k by 2. Now, I'm going to make use of a relation which was, I think, if I remember correctly, by Legendre. If that's how you pronounce his name correctly, forgive me if I'm wrong. So, according to this relation, if we have the gamma function of 2 times k, this equals 2 to the 2k minus 1 times gamma k times gamma k plus 1 by 2. And all of this is divided by the square root of pi. Now, in this case, I'm not interested in gamma 2k. I'm interested in gamma of k only. So let's divide 2k by 2. So I have to divide each k by 2. And notice by doing this, because of my interest in gamma of k instead of gamma 2k, I now have a term which is gamma k plus 1 by 2, this term over here. So that was the purpose of applying this formula, this relation. So we have, I forgot to divide by 2 over here as well. So gamma k equals 2 to the k minus 1 times gamma k by 2 times gamma k plus 1 by 2 divided by the square root of pi. Now all of this implies that if I want to isolate this gamma k plus 1 by 2 term, all of this equals the square root of pi times gamma k divided by 2 to the k minus 1 times gamma k by 2, correct? So now I can substitute this relation into the equation we derived earlier, this equation here in white. So I wrote down the two equations, the one for I and the other for gamma k plus 1 by 2, to get a better visual of things. So the first equation here, it implies that I equals, now you have a square root of pi here and a square root of pi here. So these two multiply to give you pi, multiplied by the infinite sum over k. Now you had this term of 1 by k factorial times k. You also had a 1 by gamma k by 2. And you had this term. So substituting the expression that we've just derived for it, I've already dealt with the square root of pi. Cancel that out. We have gamma k divided by 2 to the k minus 1 times gamma k by 2. And this looks pretty exotic already, but it actually works out pretty nicely. So we have pi times the infinite sum over k of 1 by, now this is k factorial, and this is gamma k. Now gamma k is an integer, right? So this equals k minus 1 factorial. And k factorial equals k times k minus 1 factorial. So you can cancel out these terms here, and you're left with k instead of the k factorial, and k multiplied by k here will give you k squared, correct? You have a gamma k by 2 here and a gamma k by 2 over here as well. So you have 1 by gamma k by 2 squared. And I almost forgot this term. 1 by 2 to the k minus 1. We have this term as well. And, okay, now what? Well, first up, I would like to take this, I would like to break this term down into 2 to the k times 2 inverse. And I can just take it outside of the infinite sum, and that will give me 2 to the k and dividing by 2 out here. Now this is an infinite sum for I. And I almost messed up big time. We had 2 to the k times 2 inverse in the reciprocal form, right? So if you take this term outside of the sum, it will be multiplied. So you have to multiply pi by 2, not divide pi by 2. Anyway, so here we have a sum, an infinite sum for I. And we can evaluate this quite nicely if we separate the positive and the, if we separate the even and odd integers. Because you're summing over all non-negative integers, right? So separate the even ones from the odd ones. So 2 pi times the sum over even integers. Now you don't have to change the variable of summation to stuff like m for even and n for odd. You don't have to do that because k is just a dummy variable. So you're summing over k, and if you want k to be even, you have to multiply k by 2. So replace all the k's by 2k. So 1 by 2k squared times 1 by gamma 2k by 2 is just k squared, and 1 by 2 to the 2k, which is in fact 4k, so let's just write it as that. Now before I write the sum for the odd integers, and before I do that, I want to first up notice some things about the even sum. So I have gamma k squared. Now this is just k minus 1 factorial squared, correct? And I have a 4k squared term here, which evaluates to, I have a 2k squared term, which evaluates to 4k squared. So 4 is just a constant, forget about it right now. Or just write it here, doesn't matter. 4k squared. If I multiply k squared by gamma k squared, I can take the k into the square term, because well, they're both being squared, right? So if you multiply k minus 1 factorial by k, then you just have k factorial, right? So this equals 4 times k factorial squared. So let's replace all of this. Let's replace all of this by 1 by 4k factorial squared. And I can just write this a bit closer. I can write the 4 outside, right? It's a constant. So 4 to the k here, and 1 by 4 outside. And now I have a lot more space for the sum over odd integers, right? So if we're summing over k, and if you want k to be an odd number, and first up I want to give myself some writing space. So if you want k to be an odd number, replace all the k's by 2k plus 1. So you have 2k plus 1 squared, 1 by gamma 2k plus 1 divided by 2 squared, and 1 by 2 to the 2k plus 1, and God, I know my handwriting is horrible. 2 pi 1 by 4 sum over k 1 by 4 to the k factorial squared, plus same reasoning for that factorial trick that I did earlier. Just notice something. Gamma 2k plus 1 by 2 can be written as gamma k plus 1 by 2, and you have the square over it as well. And you can pull out a 2 from here, and you'll have 2 squared times k plus 1/2 whole squared. And this 2 squared is just a 4, so write it out here. And you have k plus 1 squared times gamma k plus 1/2 squared. And same reasoning as before. If you have a k plus 1/2 times gamma k plus 1/2, then using the recursive relation for the gamma function, this will be equal to gamma of k plus 1/2 plus 1. And 1/2 plus 1 is 3 by 2, right? So what you have in the denominator is this function here. So let's clean up this mess now, and you're left with the sum over k of 1 by, do not forget this term, 2 to the 2k plus 1 times the reciprocal of gamma k plus 3 by 2. And now, squared of course. Now you have a couple of very, very fascinating infinite sums that can be evaluated using special functions. The first of these sums is the modified Basel function of the first kind with the parameter set to 0, or order 0, that is. And the second is the modified Strub function, and I think it was represented by L, again of the first kind, order 0. So yeah, that was fun, and I hope you enjoyed the video. Thank you, see you next time.